Thank you. Hi, my name is Jon. As you heard, that's who I am, described in a few beautiful words. So I'm here to dig into some pretty nerdy deep stuff, and I'm hoping that you're all here for it. This is not going to be Rust specific, even though a lot of the stuff that I do is Rust, but it happens to intersect quite well with people who care about Rust, tend to care about things like concurrency and parallelism and speed and data systems and algorithms. And I have a feeling that much of this audience cares about similar things, even if it's not because of the Rust programming language. So I'm hoping this will apply more broadly. You'll see a couple of slides that have tiny bits of Rust code on them, but I think you'll be able to recognize and map it sort of mentally to whatever is your language of preference. This talk is titled, Are Mutexes Slow? And there's I think it's Goodrich's law of headlines that says you can answer any such question with no. And of course, the answer to this is also no, perhaps unsurprisingly, but the reasons why are interesting because we have all observed, or at least most of us have, that a mutex was slow, that a program was slow because it was stuck taking a mutex, or mutexes were taking forever to load. So how can it be that I claim that they're not slow if I've observed that they are slow? And in fact, if you dig into and ask people what are mutexes for, you'll hear things like mutexes are slow. You'll hear that reader-writer locks are the thing that you should use instead. If you have read-heavy workloads, just use a reader-writer lock, and then you can have as many readers as you want, and the universe is happy and everything is fast. You'll also hear things like lock-free data structures are the best, or the fastest, right? And you might wonder, well, what does that mean? What is a lock-free data structure? But also, what is a lock? Like, a lock is a mutex, okay, but what is a mutex? Like, really, what's going on at the CPU level? And that's the kind of stuff we're going to dig into today to try to give you some intuition for, if you take a given concurrent algorithm, how is it going to perform? Why is it going to be slow, if it is indeed slow? And what does slow even mean? And the reality, sort of to give a preview, the reality is it's complicated, it's nuanced. There's like stuff further down that influences why these are slow. The test we're gonna use here is actually a very straightforward one. So we're gonna have a counter, and we're gonna read that counter. Nothing is going to update the counter, we're just going to read it. And we're gonna try to read it from many, many threads. This is in Rust code, but the basic idea is you have some counter, it's shared. In this case, it's atomically referenced counter, but it's a way that you can have many threads that point to the same one, the same counter. And then in the loop, we're going to take a lock on that counter, and then we're going to read that counter. That's the star guard here. The reason I have black box here is to make sure that the compiler will actually do the read. Because otherwise it would just optimize this code to this loop is a loop that does nothing, so I don't even take the lock, and then I'm not measuring anything interesting. And then I'm just gonna run lots of these in parallel. And we're gonna, there are no writes, so surely this should be fast. And let's try and see what happens if we try to use a mutex here. So there's gonna be a mutex over a counter where we just read. This first graph, very easy. It is a graph that starts very high when there is one thread. It gets about 250 million operations per second, 250 million reads per second, which if you have like a 2.5 gigahertz CPU, that means you take about 10 instructions to take the lock and do the read. That's pretty good. When you have 2 cores, it drops to about 1/10 of that. It drops to about 25 million instead of 250 million operations per second. So the graph looks like this. And then once you add more threads after that, it looks almost flat. It goes down a little bit more, but then it just stays flat very, very low. And so this might make you conclude, well, okay, mutexes are slow. This is a code that just does reads. What is the mutex doing? Why is it so slow? Just because I added more threads. What you might assume is that a mutex, which is supposed to be mutual exclusion, only allows one thread to make progress at a time. So you would not expect it to get better with more threads, but you kind of expect it to stay the same, right? The mutex should allow one operation to be happening at all times. That is not what the graph looks like. And instead, more threads give you worse performance. Now, what does this look like for reader-writer locks? Well, here's another graph, but this one's also very easy to explain because in this graph, there are 2 lines that sit on top of each other. The reader-writer lock, when you, again, only take the read lock and all you do is read, as you add more threads, the performance starts out really good, about the same as a mutex, and then gets about 10x worse. It ends up doing slightly better than the mutex, but it also, as you'll see on the graph, the reader-writer lock actually gets worse over time. So as you add more readers, the reader-writer lock ends up being worse than a mutex as you keep going. The mutex sort of drops and then stays flat. And what I'd like to sort of probe you for here is to see if you have intuition for why that might be. And my hope or the intention of this talk is that the answer is, I don't really know why that would be. That's weird. And that I can hopefully try to tell you why it behaves that way and why that's actually kind of what we would expect. So clearly, there's something else going on here. And so we need to talk about CPU caches in order to understand the sort of underlying problem here. So with this graph, you'll see, as I said, it starts out really high, and then it gets worse, and then it stays about flat. Then we will see a graph that shows both the mutex and the reader-writer lock. The blue line here is the reader-writer lock. And again, as you see, like it starts slightly worse than the mutex, but it doesn't drop quite as much. But over time, as you add more readers, the reader-writer lock gets worse than the mutex gets worse. The mutex sort of stabilizes. And so this is where we need to talk about CPU caches. And indeed, CPU caches are these things that CPUs have built into them to try to make it cheaper to access the stuff that's stored in RAM. Because the stuff that's stored in RAM is really far away from the CPU. It's far away in the sense that like the copper wire is far. And so it can take you like hundreds of instructions to reach main memory. And hundreds of instructions are an eternity for a CPU. And so you want to keep some memory much closer to the CPU, but closer to the CPU, you also have less space. So you don't get to put as much memory there. You have to be very diligent about your actual like physical space usage. And so CPUs actually have this hierarchy of caches. So you'll see that this depends a little bit on the CPU. So different CPUs have different architectures for this, but it's very common that there are 3 levels of cache. L1 cache is very close to the CPU. It's like soldered onto the CPU. L3 cache, on the other hand, is pretty close to RAM. It's not as far as RAM, but it is closer to RAM. The L3 cache is usually shared amongst all of the cores of your CPU. The L1 cache is not shared. The L2 kind of depends on the CPU. It's just somewhere in the middle between L1 and L3. Its latency is somewhere between L1 and L3, and these also increase in size as you go up. So the L1 cache is very small, the L2 cache is a little larger, and the L3 cache is decently large, and then RAM, of course, is humongous, as we all know. Now, what happens if one CPU has some bit of memory, like the counter we were talking about, in its local cache? And then some other CPU core wants to read that memory, what happens? Well, there needs to be some kind of cache coherence protocol to negotiate between them who's allowed to write it when, and to make sure that the right value makes it back to RAM eventually. And that protocol is called MESI, M-E-S-I. There are a bunch of variants of it, so there's also MSI and there's M-E-ISI and there's ME, there's like a bunch of different various combinations of letters protocols, but most of them are MESI-like. MESI stands for modified, exclusive, shared, and invalid. And those are the 4 states that something can have in the cache. The cache keeps an entry for, you can think of it logically as like every piece of memory, like every address in RAM. The reality is it's not actually every address in RAM, it's every chunk of RAM. So the CPU has this notion of cache lines. So it takes all of your main memory, it divides it into 64-byte chunks, and those 64-byte chunks are a cache line. And so you took RAM and you just like write it out, like the first 64 bytes is one cache line, the next 64 bytes is one cache line, and so on. And the cache keeps track of memory on the sort of boundaries of cache lines and keeps track of which CPU cache has exclusive access to which cache lines, or which CPU cores share access to a given cache line. And this is where we get into some really interesting stuff. So when the state is modified, it means that I have the only copy. So if it's in my cache as a CPU core and it's marked as modified, I have the only copy and it is dirty, as in it differs from what's in RAM. So that means if anyone else were to read it, not only would I need to give up my permissions, but I would also need to write it back to a place they could read it from. Exclusive means that I have the only copy, but it's not dirty. So if someone else wants it, they can just take it without having to talk to me first. Or they would need to make sure that I move mine to invalid, but they don't need any data from me, because that data hasn't changed. Then we have shared, which is multiple caches have entries for these, and those cache entries are all the same. They all have the same value. Otherwise, shared would not be a legal state. And then we have invalid, which is I don't have a copy of this cache line. This could be that like it used to be, like it is in my cache in the sense that I had it previously, but I'm not allowed to use that cache line entry anymore. Because it's been given away to someone else to be exclusive, for example. If you, for example, are a core and you have a particular cache line in the shared state and you want to write to it, the protocol requires that you first make sure that no one else has it in the shared state, so that only you do, and then that everyone realizes that you have now moved it to the exclusive state. And at that point, you're allowed to read and write it as you wish. You don't have to tell anyone that you're now modifying it, even if you did multiple modifications. And then eventually, if someone else wants to modify or read that cache line, they have to tell you to convert it back into shared so that they can then get a copy that they can read from, but cannot write to. And the interesting observation here is that writes to shared data requires coordination between cores. If I have a shared version of a cache line and I want to modify it, I must talk to basically all the other cores because I need to make sure they know not to modify it and they know not to read it either. And this is where some of that cost comes from. There's a bunch of cross-core communication. And in fact, if we look at a reader-writer lock, then a reader-writer lock, the implementation of taking the read lock, is actually that you increment the reader count by 1. So there's a counter inside of the lock, not the counter that we're benchmarking here, but inside of the lock. There's a counter that keeps track of how many reader threads are there. And that counter, in order to take the read lock, you have to write to. And so if you have 100 threads that all want to take the read lock, they're all doing a write on a shared field. This means that every core needs to, at some point, get that one in exclusive mode, update it, and then make it shared again. And then the next core that wants to read the lock needs to get in exclusive mode, modify it, and then share it again, and so on through all 100 cores. And so in a way, you can think of this as there's a sequential part of every reader-writer lock. But after you've done this, now you don't have to talk to the other cores, but you do have to do it for the setup. So let's walk through what that actually looks like. Let's look at if we have two readers that are both trying to acquire a read lock. So here we have core 0 and core 1. The S here is the cache line state for the cache line that they're operating on, whatever that might be. And then the note is just to explain what's happening. So initially, let's say that core 0 has exclusive access to this cache line, and core 1 does not have a valid entry. And then core 0 wants to do the fetch add, right? Because it wants to acquire the read lock. Well, that's easy. It has exclusive access, so it just marks it now as modified and then updates the 1. No problem, there's no cross-core traffic. Now, core 1 wants to acquire the lock. Well, it observes that this entry in the cache is already modified by core 0. And so there needs to be now a write back from core 0 to core 1's cache to inform it of the updated value, because the value got updated at step 1. So that edit needs to be communicated to core 1. When that's happened, the protocol has some various kinds of optimizations, including things like you don't need to go via the shared state. So you can just give the data over and say, I'm sort of giving you ownership alongside the data. And so at this point now, core 0 has invalid and core 1 has modified because it got to do its fetch add. And then core 0 wants to release its read lock. Well, the whole process happened again. So now I need core 1 to write back to core 0 so the core 0 can get an exclusive state and then decrement the counter of reader nodes. And so what we see is if you have one instance of like, I want to acquire the lock and release the lock, you actually require 2 cache line transfers. One to get it so you can do the add, and one later so you can get it to do the release, the subtraction. And each of these transitions costs about 30 seconds. So there's sort of this cache line ping pong ends up being a really expensive operation because talking to different parts of memory costs different amounts of time because they're different distances from the cores. You'll see here that if you want to read something or access something in L1 cache, it's 1 nanosecond. It's like no time at all. But if you have to go to cross-core communication, which is what you need to do in order to do that cache line transfer, that takes about 30 nanoseconds. And now imagine that I have to do 2 of those, one's to acquire and one's to release. So that's 60 nanoseconds in the good case. Accessing main memory is 100 nanoseconds. That's the thing that we think CPUs think take forever. And we're already over halfway there just by acquiring the read lock alone. The other thing that I think is really interesting here is that for mutexes, it's not quite as bad. For mutexes, when you acquire the lock, you hold the lock, and you know that no one else is going to try to increment that counter from you because, well, they can't acquire the lock. So the problem, in a way, is reader locks. Because if you have an exclusive lock, when you release, you know that you're still the owner of it. Someone else might have gotten a shared copy, but they will not have an exclusive copy. They can't have anything to write back because all they can have done is read. And so reader locks almost scale worse than mutexes here. And this is one of the reasons why that reader lock thing gets worse, is because as you get more readers, they contend more and more with each other. Whereas if you have many mutexes, they don't really contend with each other because they're fine with going one at a time in a sequence and not causing all this cache line ping pong. The reason why people don't think about this problem that much is because usually when you interact with locks, you have a bunch of code in there. Like after you take the lock, you run a bunch of code and then you release the lock. And so the cost of acquiring the lock is not really something that matters that much to you. But this is not true if you have short critical sections, like short amounts of code between acquiring the lock and releasing it. Because if that's the case, you're going to find that the time it took for the cache miss is more than the time it took for you to run your code. And so in general, you'll find that the overhead of using a lock goes up the more you need that lock to be fast. Sort of the inverse proportion of what you want here. For longer things, mutexes are totally fine. Use them as much as you wish. It's primarily when you hit those hot critical path loops where you also know you have contention, where you need a mutex because there's contention, that a mutex doesn't really work very well. And this is also why real-world code tends to not worry too much about these problems, and it's only when you start writing pretty specialized code in those deep hot loops that you need to start knowing about things like messy. And so I want to now take a sort of sidestep to, well, what can you do instead? So if you can't use mutexes and you can't use reader-writer locks, what can you use? And I'm not going to propose that this is the correct algorithm. As I'll get to later, this has a bunch of trade-offs too. I just want to sort of inject in your mind other kinds of alternatives to sort of let you think about what else could you do that doesn't necessarily have this problem, but might have other problems. So I want to talk to you about the left-right data structure. The left-right data structure is something that I used in my PhD research where I had enormous amounts of readers and very few writes. So I basically hit this problem, and the thing that I did when I held the read lock was a hash map lookup and then nothing else. So the read was very, very short, and so the overhead of the reader lock was just killing me, and so I needed something else. So what's interesting here is it was trying to solve this problem of why do all the readers need to access a shared cache line? It feels like if the readers are supposed to be independent, they need to have their own cache lines, not a shared one. So how can you design a concurrency primitive that is still safe for having there be many reads and a writer, but is safe in such a way that like the readers are cheaper and the writer has to do more work? Because my writes happened relatively infrequently, so I was willing to pile more work onto there if the readers could be highly parallel. So the way left-right works is that you keep 2 copies of your data. You keep a left copy and a right copy. You have a pointer in the center, sort of an atomic pointer that every reader and the writer has access to, and that pointer points to the side that the readers should read from. It points to the copy that the reader should read from. The writer will always be modifying the one that's not pointed to by the pointer. And then when the writer has made a bunch of modifications to the writer-owned write copy here, then it switches the atomic pointer over to now point to the other side. When it points to the other side, then now all of the readers will start reading the right-hand side copy, and the writer can eventually start modifying the left-hand side copy. And the intent here was the readers might not need to coordinate at all, because the writer doesn't really care what the readers are doing, with the exception of it needs to know when it's safe for it to start modifying the copy is switched away from. So imagine you have a bunch of read threads that are reading the left copy sort of before we swap the pointer. And then the writer swaps the pointer, those read threads are still in the left copy. And so left copy. But so something has to tell the writer, all the readers have read the updated pointer value now, they're in the right copy, and so it's fine for you to just now start modifying the left copy. So some mechanism is needed here, some synchronization primitive. And it turns out that you can do this by giving every reader their own cache line. They have their own counter that basically keeps track of how many times they've read the pointer. And then the writer's job is going to be look at the counter for every reader. It has a giant for loop where it loops over all of the readers that exist, reads all of their individual counters, and observes that all of them have changed by at least one since when the pointer was swapped. The reason this works is because when you switch so you read all you switch the pointer, then you read all of the counters, and then when you read them again, if they've changed by at least one, it means that that reader has read the updated pointer, is now doing a second operation. And if it's read the pointer, it has read the changed pointer, and therefore it's no longer in the original map. The interesting thing about this design is the readers do not share state with each other. The readers just keep their own counter for how many times they have read the pointer. They do not need to talk to each other. In other words, if we think back to the Messy protocol, this means that the core that's running any given reader thread can just keep that cache line in the exclusive state. Never has to be shared, except for when a writer wants to sort of do the pointer switch. Because then the writer thread, the core that runs the writer, has to read the counter from every reader, and then, turn it into the shared state, read the value, and then it goes back to the reader again to update. But only when the writer wants to contend with the readers does anything interfere with what the reader wants to do. Otherwise, the readers are completely independent. And readers become even better than that. They now don't have to wait for anything. They don't have to wait at all. Even if there is a concurrent write, they can just keep reading their copy. So the reads end up being lock-free. The reads do not pause for anything. In fact, they are wait-free. They do not wait at all. They don't take any locks. They don't have any loops. They just read the pointer, bump their counter, and then access the data. And that's all they need to do. And the net result of this is you get a graph that looks like this, maybe. Yeah. And so this graph is linear. It goes up and to the right in exactly the way you would hope when you increase the number of threads. And again, we now have the intuition to understand why. It is because the reader threads, the cores that run the reader threads, do not have to coordinate, and therefore can just run fully in parallel. Yep.
If one of the threads is
Here, take this.
one of the threads is dormant for some reason, or maybe doing a lot of work, then they just still hold the old reference and don't increment it? Is that an issue?
So the algorithm is slightly more complicated than I told you. So the algorithm is actually that a reader will increment its value, its counter value, before it starts an operation, and again at the end of its operation. And so what the writer needs to look for is any reader where the number has gone up or where it's even. And that way you know that like dormant readers are not a problem. Readers that continue to hold on to their access is a problem because they prevent the writer from starting to modify the other one. But it doesn't prevent readers from continuing to read. It just prevents the updates to the map. So the next thing you'll observe here is like the number here is pretty high. Like this is 3 billion operations per second that we get to read. But again, it's just because we had wavehand about 10 cores. And so it should be about 10 times what we had at 1 core, which is not what you get with a reader-writer lock, even though the name sort of implies you might. And the key here, though, is that this only works if writes are rare. If writes are rare, then this performs really well, really, really well, because the only writes can make contention in this system. On the other hand, if writes are not rare, it doesn't perform any better than what you get with a reader-writer lock. And in fact, if you start flipping, I didn't include that in this graph, if you start flipping the ratios, you do more writes than reads, this does worse, because the writer has to do a bunch more work, and you don't really get the speed performance win from the readers being lower contention. And the intuition here for why the reader-writer lock gets worse is, again, the same one we talked about earlier for why the reader-writer lock graph goes down, is that the reader-writer lock gets punished more as you add readers. So here, there are 9 times more readers than there, right? So in that case, you would expect to get a slowdown because they contend more with each other. And I want to give you a debugging story here because there's a useful insight as part of this. So while benchmarking left-right to produce the previous graph that went up and to the right linearly, I discovered that it did not go up and to the right linearly. There was sort of this weird dip where I was expecting it to keep going linearly, and instead it dropped significantly, dropped by like 10x when I got to 4 cores. And I was like, why is this happening? This shouldn't be happening. It does not match my intuition for how CPUs work. And it turned out that the problem here was not like crossing between NUMA architectures or like you ended up going to like a different CPU package that's further away. Like I went through all of these like ideas of maybe it's this, maybe it's that. Turned out it's actually pretty simple. And it's something that you like, it's one of the first things you learn when you deal with concurrency at this level. It was something called false sharing. False sharing happens because, remember I said the cache doesn't operate on individual memory addresses, it operates on cache lines, 64-byte lines. Well, a counter, you can have more than one counter in 64 bytes. And so if you get unlucky, the counters for, so this is like not the counter we're benchmarking, but the counter inside of left-right, if multiple threads have their counters on the same cache line, then it doesn't matter that one is only modifying this counter and one is only modifying this counter. They're on the same cache line, and the ownership, the messy ownership, is determined based on the cache line. So when one writes and then the other writes, the cache line will still bounce, even though they update distinct parts of that cache line. And so the fix was like a one-line fix. It was to add 64-byte alignment to the type that holds the counters, because now they must be on different cache lines, and the problem went away. Like it was just that. There's now a new release of left-right that has this fix in it, so now it should go up and to the right for you as well. I contributed it upstream to myself. But there's an important distinction here, which is that lock-free does not mean contention-free. Just because there are no locks does not mean that the CPU isn't going to punish you because you made memory move around a bunch more. Like, moving things across copper wires is expensive, and if you can avoid doing it, you will have a faster program. This is also why it's important to know about this stuff, to have some amount of the intuition for why did this thing perform that way, or why did it not perform the way that I wanted to, and try to like debug in a way where if you like threw this at like perf or something, it wouldn't really tell you, because the thing that's going wrong is like the CPUs have to talk too much to each other, which is sort of a layer beyond the abstraction layer that we usually reason at. And what I want the sort of takeaway of this talk to be is that I want you to start choosing a little more wisely. If you have to write code that needs to be highly parallel, highly concurrent, and is sort of sitting in these critical loops, then it's not as though you should just take the first algorithm you find, even if it's one that's been benchmarked against really good performance reviews, or like you like look on the OCaml version of Crates.io for the fastest mutex or the fastest reader-writer lock, and then you just use that one. Because the reality is you have to pick the algorithm that best suits the sort of data transfer patterns that your application has. Because the way we make concurrent programs faster is that we pick algorithms that align with what your program wants to do. You make use of every single weird oddity that your workload has. All of those can be exploited to make the algorithm slightly better for your use case. And I mean, left-right here is a really good example. It is not a drop-in replacement. There are a bunch of things that left-right does that you will not want to do for most applications. Obviously, it keeps 2 copies of all your data. That's pretty expensive. Readers can see stale data, right? So the writer gets to modify the stuff and thinks it's modified the stuff, but the readers don't get to see it until the next time they read after a pointer swap. Left-right has a mechanism where the writer can say, I now want to wait, don't return until all the readers have moved on. So you can do that, but that then comes at additional cost to the writes. It's also single writer only. You cannot have multiple writers in left-right. It assumes that there's only one. If you want multiple, you have to put the right side of it in a mutex. And then now you have a mutex on top of a concurrent data structure and you're gonna get sadness. It's possible, but it's not what it's designed for. Operations also have to be deterministic so that you can't take an arbitrary data structure and turn it into a left-writable data structure. The reason for this is because when you have this left-right split, imagine that you do a bunch of operations to the for you, left side, left copy. Well, and now you switch the pointer over. Now you need to take the right copy and apply the same changes to that right copy as you applied to the left copy while it was the active one. Because the right copy is sort of stale now. It didn't see those updates. That means you need to be able to log, keep a log of the updates that have been applied here but haven't been applied here. And then you need to be able to apply them to the other one, and they need to have the same result. Otherwise, you would end up with the 2 copies having different state, and then readers will get super confused. And so you can only do this for data structures where you're able to keep an operational log that's deterministic in how it affects the data structure. Not all data structures have that property. Writers also have to wait for all readers to exit, which may or may not be a problem for you. Maybe you actually want them to be able to just run a bunch of writes while the reads are going. We don't really care. Maybe that's the application you want. You want weaker semantics. You could do that and probably build an even faster data structure. But the nuances of what you need is what gives you the performance. There's a bunch of other stuff, it's not linearizable, so it's only eventually consistent, which may or may not be a problem for you. For example, I would not use left-right for financial transactions, but I would use it for things like caches or lookups or those kinds of things. So your mileage may vary. The reality is that every solution has trade-offs here, right? Mutexes are the correct choice for a bunch of concurrent algorithms. Just like reader-writer locks are the correct choice for a bunch of algorithms. And left-right is the correct choice for a bunch of them. But it depends on what your needs are. And that's what I really want you to take away from this. Some of the questions I would recommend that you try to ask yourself here is what is my ratio between reads and writes? That's tend to really affect what algorithm you use. You should ask yourself, how long is the code that I want to execute in a synchronized way? Because if it's short versus long, that changes the sort of budget you have for the synchronization. Think about how many threads you're gonna have. If you're gonna have 3 threads, none of this matters, right? If you care about it, it should be faster at 2 threads than 1, then okay, maybe it matters a little, but you saw the dramatic graph, it can matter, but usually that's not the kind of scale or concurrency where this stuff really becomes relevant. Can I tolerate eventual consistency? Do I need strong consistency in my reads versus my writes? Do I need, for example, to be able to read my own writes? So imagine that I, as the writer, I make a modification to the data structure, and then I try to read from the data structure. Should I be guaranteed that I read the modification I just wrote? Left-right does not give you that guarantee, because you might read from another map that's the other one than where you were writing. But if you need that, well, then you need to take that into account in your design of the algorithm as well. Do you need linearizability? Do you leave even stricter guarantees about what 2 threads can possibly see in relation to another? Which interleavings are possible? And I'm not gonna teach you all of those things now. It's more that these are the kinds of things you should ask yourself if you want to go the sort of step beyond of just using an off-the-shelf concurrent algorithm. Always measure before you start optimizing these things. And the real lesson is that it's not about locks. It was never about locks, right? Coordination is expensive because of cache coherence. because of what the CPU needs to do to guarantee that your program executes correctly. The locks are just the interface you happen to be using. And there are a bunch of other ways in which CPU caches can burn you as well, but this is the one you're most likely to run into without necessarily realizing that that's the thing that bit you in the ass. A couple of other articles that are really useful that talk about more of the details here. This top one I really like, which is a breakdown of like how long does things take in the CPU? Like how long does it take to read from disk versus talk to your L2 cache? Versus send a TCP packet, versus send a TCP packet to the other side of the world. Like, what is the relative timescale of these things? And some of the other ones are also just interesting other data structures you might be able to make use of. So for example, scalable reader-writer locks talks about a way where you take a reader-writer lock and instead of having one counter for the number of readers, you have one counter per core per reader. So there's like, you don't have as many, you don't have per reader, you only have per core, and therefore most operations are core local and the writer walks across all of them. And so this also can be the kind of thing that like, maybe that fits your use case better, but ultimately, I hope you give some of these a read to give you a better idea of what the trade-off space looks like and what options you have if you wanted to write some really concurrent code. That's all I have for you. Thank you. Questions? Do you have questions now? Because you had early questions earlier.
I'll ask one more. I'm not sure how helpful this will be, but have there been any interesting hardware innovations for parallel programming? Like somebody released some new operation that made like mutexes like 10 times faster because it was a native operation.
So I wouldn't say there's been like revolutionary new things where like just whole workloads are now 10x faster. But the Messi protocol started out as the MSI protocol, and then they added E because they found like the exclusive state, because they found that certain workloads could avoid like half of their cache line contention by having this. And I think they're up to like 7 or 8 letters now in some of the more modern CPU architectures. Part of the problem is these are often proprietary protocols. Like we know that they exist because they are documented in the spec for the CPU, but they don't tell us like, what does the CPU do internally? They just sort of tell us how to think about it. Some of them are like earlier versions were open, but later versions, we don't know exactly what the CPUs are doing, but we know that they work roughly like this, but nothing where we've been like, this is crazy. I think the closest I would say is there's been some work on like, when they build CPU packages to build them more in 3D. And the reason 3D is cool is because you can have shorter distances to things, right? So you can put your cache above your CPU, and so now that cache can be bigger because it has more space to grow, and so now you have a bigger L3 cache, and you can maybe share it among more cores. This is like the, for AMD processors, they have this thing called 3DX, I think is like, you can buy like their CPU or the same CPU with 3DX in the name. And the 3DX is just like, they stuck an L3 cache on top. And so it had more L3 cache now. And that ends up helping for some of this stuff, right? Because it means you don't need to go as far when you need to access data than in a core written, for instance. But not really anything that's been mind-blowing. There has also been some cool work on fetch add. So one of the things that's neat about fetch add is that it's fully commutative, right? The fetch add operation is add 1 and tell me what the number was when you added 1. And what you can do is you can actually have lots of CPUs sort of pool their fetch adds, and then one core runs all of them and then sends the results back to the other cores. And so that way you don't have to bounce the cache line around as much. I don't know of any current platforms that do this optimization, but I know for a period they did. And again, part of what makes the answer here unsatisfying is that so many of these systems are proprietary. And so it's just, we don't necessarily know. We know what was published many years ago, and then we don't know how much of it is still in use. So a lot of it is also speculation.
Thank you.
Yeah. Cube.
How would performance of left-right change if you had many readers joining and leaving over time?
For which data structure?
Oh, for left-right.
for left-right, if you have many readers joining and leaving over time, so the way left-right is currently set up is that the list of readers is held in a mutex. And so if a reader wants to join, it has to take that mutex, allocate its own counter, stick it into the list of that mutex, and then unlock the mutex. And the writer uses that same list to figure out all the readers to read from. But the readers, once created, never have to access the mutex unless they want to go away. And in fact, even if they go away, they could just leave their stuff there, because then it's even, and so the writer ignores them, but they should clean it up. If this ends up becoming a bottleneck, then you could easily make that list be a lock-free linked list instead, because you only ever need to add to it or walk it. You never need index lookups. And so you could make it, like, you could allow readers to join in parallel as well. The only thing you'd have to be a little bit careful about is to make sure that the writer reads all of the counters after it does the swap. If it reads any of them before the swap, then it can get confused. But should be doable. It's just, I haven't needed that optimization because readers joining has been not the bottleneck.
Kind of getting at a similar thing to the hardware question, how much variety is there in implementation of mutexes on a software level, and how much of a difference does that make?
On the software level, mutexes are a little bit of a weird beast. So there was a period of time where there were a lot of, like, every language had their own implementation. And then a bunch of companies wrote faster implementations they wanted to use. And then eventually we got better operating support for mutexes. So futexes, for example, are fast user space mutexes in Linux. And you can usually just use those. Like, you don't really need a lot of packaging on top of it. And then in later years, we found people who've tried to do even, like, different kinds of optimizations on the mutexes. So they're not necessarily about decreasing the contention, because that's gotten to the point where, like, it's just the baseline contention. You can't really do any better. But they try to decrease the size of the mutex. So there are data structures, for example, where I think the size of a mutex is 1 byte. But they can still make it work. Is it 2 bits now? We're down to 2 bits? Yeah. But the problem, of course, is then if you start packing many of them together, then now you hit the cache line problem. And so now they're contending with each other, and so it doesn't really help to make them smaller unless you strategically choose mutexes that are, like, don't contend with each other on the same cache line, and you can see how deep this rabbit hole goes.
I see.
But in terms of quality of implementation, I would say they're all roughly equivalent now. The exception is when you start looking at things like reader-writer locks, where different operating systems have very different mechanisms for them, and they need to, like, just like mutexes, they have to hook into the operating system to make sure that a thread that can't take the lock right now, is unable to take the lock. For example, a reader comes, but a writer is currently holding the lock. That thread wants to go to sleep. So it needs to talk to the operating system, and then the operating system needs to have a mechanism to wait it back up. And that, the sort of how reader-writer locks should work in the operating system, I think there's still some iteration on. Also in user space, like, how you place, how can you take the reader-writer mechanism the operating system gives you and make it more scalable, for example, by keeping multiple copies, 1 per core, where what, like, a given thread will do is look up what core it's on, pick that reader lock, and then take that one. And so that way you can like build better things on top of the operating system, so that there's enough more sort of design space for reader-writer locks than there is for mutexes.
Nice, thanks.
Is that a question back there? No.
You mentioned in your earliest code example that you needed to provide a little compiler hint to prevent the compiler from optimizing away your entire benchmark setup. I'm curious about, like, what sorts of optimizations exist in compilers around mutex handling, and if there are any particularly surprising or shocking ones you've seen.
So compilers tend to be kind of careful around mutexes because users tend to assume that they will operate in certain ways. But the way they do that is usually by having barriers. So there's, like, I don't want to get too deep into, like, the different kinds of barriers and like the various like seek, const versus acquire versus release and stuff. That's gonna get so painful, but the compiler basically injects these little special sparkly bits in your assembly in the generated code, where sometimes it's for the compiler, sometimes it's for the CPU, sometimes for both, that says don't move, you're not allowed to move reads before this point, or you're not allowed to move writes after this point, and vice versa, to try to basically ensure that, for example, if you take a lock and then you read something after you took the lock, the CPU can't do out of order execution and do the read before it took the lock, because that would be not okay. But that's not really it's not really like a compiler thing. It's more of the implementation of the data structure needs to know to inject those sparkly bits to make this work correctly. And if you don't, you would end up with a mutex that looks like it works correctly, but sometimes you read the value before you got the lock. Compilers do tend to be like very good at optimization, a little bit better than we would like them to be, right? But we would rather that than the other way around, probably, maybe. That there has been an argument in like recent years for dumber compilers, because they're like, CPUs have gotten faster, so make the compilers dumber so that we can do more stupid shit and have it do the correct thing. But I wouldn't say like compilers are, they're not like deeply tied to how mutexes work at all. I think we're good. All right, thank you everyone.